September 3rd, 1942. Bethpage, Long Island, New York. The telephone call lasted exactly 11 minutes, but those 11 minutes would fundamentally reshape aerial warfare in the Pacific. Rear Admiral John McCain, Deputy Chief of the Navy's Bureau of Aeronautics, posed a question that seemed absurd on its face. Can Grumman produce 2,000 fighters by mid-1943? The man on the receiving end, Leon Jake Swirbul, Executive Vice President of Grumman Aircraft Engineering Corporation, answered with brutal honesty. I don't know. We've never built at that scale. At that precise moment, Grumman was producing exactly 3 F6F Hellcat fighters per month. The Bethpage plant employed 1,200 skilled workers, each trained for years in traditional aircraft construction methods. Each Hellcat required approximately 200 man-hours of labor, from fuselage assembly to final test flight. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The mathematics of defeat were writing themselves. At 3 fighters per month, producing 2,000 aircraft would take 55 years and 7 months. The Navy wanted them in 9 months. The difference between those two numbers represented the distance between victory and catastrophe in the Pacific. McCain wasn't calling to negotiate. Reports from the Pacific were catastrophic. The Mitsubishi A6M0 dominated the skies. Current American fighters, the F4F Wildcat and F2 Buffalo, were outclassed in speed, maneuverability, and climb rate. American pilots were dying at an unsustainable rate. The F6F Hellcat represented hope. Designed specifically to defeat the Zero, it featured a Pratt & Whitney R2800 engine, producing 2,000 horsepower, a top speed of 380 miles per hour, and armament of 650 caliber machine guns. Flight tests showed it could outperform the Zero in speed and firepower. But a superior fighter that exists in only 3 examples per month wins no wars. McCain needed hundreds of aircraft, then thousands. He needed production that could replace losses, equip new carriers, and saturate Pacific skies with overwhelming numerical superiority. Swirbul hung up the phone and immediately summoned Roy Grumman, the company's founder and president. The two men had known each other for 20 years. Grumman had founded his company in 1929 in a garage, designing seaplane floats. By 1942, Grumman Aircraft had become a major manufacturer, though still relatively small compared to giants like Boeing or Douglas. Roy Grumman listened to McCain's requirements and asked the obvious question. How? We can't simply hire more skilled workers. Training takes years. We can't expand the factory fast enough. And even if we could, current methods can't produce faster. Swirbul also called William Schwendler, Grumman's chief production engineer. Schwendler had joined the company in 1936 and had supervised construction of every Grumman aircraft type since. He knew intimately every aspect of fighter manufacturing. The 3 men gathered in Grumman's office within the hour. They faced an impossible proposition. The Navy wanted 2,000 combat-quality fighters. They wanted them in less than 9 months. And they wanted Grumman to develop production methods, train workers, and deliver finished aircraft starting from a capacity of 3 per month. Schwendler's first question cut to the heart of the problem. What's the current production time per aircraft? Swirbul had done his research. 200 man-hours per Hellcat, hand assembly throughout the plant, components individually fitted. Each aircraft is essentially unique. Schwendler did the mathematics immediately. At that rate, 2,000 fighters would require 400,000 man-hours. Even with 3 shifts working 24 hours daily, that would take years. The Navy wants them in 9 months. Swirbul's response would define the entire program. Then we don't build fighters the traditional way, we build them our way. If they want 2,000 Hellcats in 9 months, they need to accept automobile production methods, which means we need to rethink everything. The resistance came immediately, not from the Navy, but from Grumman's own engineers. Senior designers argued that aircraft weren't automobiles. Fighters faced stresses that cars never encountered. Tolerances had to be tighter. Quality control had to be absolute. Mass production would create catastrophic quality problems. Swirbul listened to every objection, then asked one question. Can anyone else deliver 2,000 fighters in 9 months using traditional methods? The room fell silent. Nobody could answer affirmatively. We'll figure it out, Swirbul said finally. That phrase would become the program's unofficial motto. They didn't know how to mass-produce fighters. They didn't know if their ideas would work. But they knew that failure meant American pilots would continue dying in inferior aircraft while waiting for reinforcements that would never arrive in sufficient numbers. In the days following McCain's call, Swirbul, Grumman, and Schwendler toured the Bethpage plant with fresh eyes. They watched workers assemble Hellcats using methods unchanged since the First World War. What they saw convinced them that traditional aircraft production was fundamentally incompatible with modern war's demands. The Bethpage factory in September 1942 resembled a watchmaker's workshop more than an industrial production line. Highly skilled workers laboured around stationary fuselages, each performing complex operations requiring judgment and expertise. A master assembler might spend 3 days perfectly fitting a wing section. Schwendler timed every operation. He discovered that 60% of production time went to custom adjustments and modifications. Components manufactured to military tolerances varied so widely that assembly required constant adaptation. 2 wings carrying identical part numbers could differ by several millimeters in critical dimensions. This variability demanded craftsmen, not workers. An assembler needed to know when to file a part, when to shim it, when to reject it entirely. These decisions couldn't be codified in simple instructions. They required years of experience and a trained eye. The fuselage assembly illustrated the problem perfectly. Workers hand-fitted aluminum skin panels to the internal frame structure. Each panel required trimming, drilling, and adjustment to achieve proper fit. Riveting demanded skilled judgment about pressure, angle, and spacing. A poorly set rivet could cause stress cracks or structural failure. Wing attachment represented another bottleneck. The wings bolted to the fuselage at 4 mounting points, but achieving perfect alignment required hours of measurement, adjustment, and remeasurement. Workers used shims, thin metal spacers, to compensate for tolerance variations. Each aircraft needed different shimming patterns. Grumman visited other manufacturers for comparison. At Vought in Stratford, Connecticut, he saw similar methods for the F4U Corsair. At Republic in Farmingdale, the P-47 Thunderbolt was built with the same craftsman process. At Bell in Buffalo, the P-39 Airacobra required identical meticulous hand-fitting. The entire American aircraft industry operated on this model. Aircraft were treated as precision instruments, each requiring individual attention. This approach produced excellent fighters, but in pathetically small quantities. European manufacturers followed identical methods. British Spitfires were hand-assembled by skilled workers. German Messerschmitts required similar craftsman labour. Japanese Zeros were built using traditional techniques, refined over decades. Every major power viewed fighter production as specialized work, requiring master craftsmen and years of training. Schwendler recognized this as the fundamental barrier. We can't scale craftsman production, he told Grumman and Swirbul. Skilled workers take 5 years to train fully. We don't have 5 years. We don't even have 5 months. The heretical idea emerged gradually through multiple discussions. What if fighters could be built like Ford built automobiles? Henry Ford had revolutionized car manufacturing by breaking complex assembly into simple, repeatable operations performed by semi-skilled workers on moving lines. Could the same principles apply to fighters? The concept seemed impossible to traditional aircraft engineers. Automobiles operated at low speeds on smooth roads. Fighters flew at 400 miles per hour through violent maneuvers, generating forces that would destroy any car. The comparison was insulting to the aircraft manufacturing profession. But Schwendler saw underlying similarities that others missed. Both automobiles and fighters were complex mechanical assemblies built from thousands of components. Both required precision manufacturing and quality control. Both needed to be reliable and maintainable. The only fundamental difference was the operating environment. If components could be manufactured to tighter tolerances, automobile-level precision, rather than traditional aircraft tolerances, then they would fit together without adjustment. If assembly sequences could be standardized and simplified, then semi-skilled workers could perform them after brief training. If the fighter could be broken into major sub-assemblies built separately and joined at final assembly, then multiple work teams could operate simultaneously. This was the forbidden idea. It violated every principle of traditional aircraft manufacturing. It challenged the professional identity of skilled aircraft workers. It required redesigning the Hellcat itself, changing specifications that the Navy had already approved. It meant gambling the entire program on unproven production methods. When Schwendler presented the concept to Grumman's engineering staff, the resistance was fierce. "Aircraft aren't automobiles," senior engineers insisted. "You can't mass-produce fighters. Quality will suffer catastrophically. Pilots will die because of production shortcuts." Swirbul listened to every objection, then asked his signature question. "Can anyone suggest an alternative that delivers 2,000 fighters in 9 months?" Once again, silence answered him. The impossible remained impossible under traditional methods. The forbidden idea was the only idea that offered any possibility of success. September 15th, 1942. Jake Swirbul made a decision that could destroy Grumman Aircraft or save the Pacific Fleet. He authorized what he called the Production Engineering Group, a secret team tasked with completely redesigning the F6F Hellcat for mass production without Navy approval. The secrecy was necessary. Navy specifications for the Hellcat were contractually binding. Any design changes required formal approval through the Bureau of Aeronautics, a process taking months. Swirbul didn't have months. He had weeks before production commitments became impossible to meet. So he decided to violate the contract, redesign the fighter, and present the Navy with accomplished facts. William Schwendler led the Production Engineering Group, assembling 15 engineers sworn to confidentiality. They commandeered a locked room in Building 3 at Bethpage, working 18-hour days, often through the night. Security guards were told the room contained classified Navy projects. Technically true, though the Navy knew nothing about it. Schwendler's first mandate was radical simplicity. The Hellcat contained 3,214 individual components in its current design. Each component had to be evaluated for mass production compatibility. Could it be manufactured to tighter tolerances? Could it be made interchangeable? Could it be simplified without compromising performance? The group began by breaking the fighter into 5 major sub-assemblies that could be built independently and joined at final assembly. The fuselage became sub-assembly 1. The wing group, both wings connected by center section, became sub-assembly 2. The engine and cowling became sub-assembly 3. The tail group became sub-assembly 4. The landing gear became sub-assembly 5. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. This modular approach was heretical. Traditional aircraft were built as integrated wholes, with components added progressively to a growing assembly. Schwendler proposed building major sections separately, allowing parallel work by multiple teams, then joining them in final assembly. The concept worked for automobiles, but had never been attempted with fighters. Each sub-assembly required detailed analysis. The fuselage presented the greatest challenge. Current construction used hand-fitted aluminum skin panels riveted to an internal frame. Schwendler's team redesigned the fuselage using standardized panels manufactured to automobile-level tolerances plus or minus 0.005 of an inch, rather than the traditional plus or minus 0.20. This tighter tolerance seemed impossible to aircraft engineers. Aluminum sheets varied in thickness, forming dies wore during production. Temperature changes affected dimensions. Achieving consistent 5,000th tolerances would require precision tooling and rigid quality control, unprecedented in aircraft manufacturing. But Schwendler had studied Ford's methods. Automobile manufacturers routinely held 5,000th tolerances on engine components, facing far higher stresses than aircraft skin panels. The technology existed. It simply had never been applied to fighters. The wing group redesign was equally revolutionary. Current wings required custom fitting to each fuselage. Schwendler designed a standardized center section with precision mounting points. Any wing group would bolt to any fuselage without adjustment. The concept required redesigning the wing attachment structure and establishing new manufacturing tolerances, but it would eliminate days of fitting time. The engine installation underwent similar transformation. The Pratt & Whitney R2800 engine was mounted in a complex cowling requiring extensive hand fitting. Schwendler's team designed a modular engine mount and standardized cowling that allowed the entire power plant to be installed as a complete unit in under 2 hours. Landing gear presented special challenges. The Hellcat used a retractable tricycle gear with complex hydraulic actuation. Current assembly required skilled mechanics, spending days routing hydraulic lines, adjusting mechanisms, and testing operations. The production engineering group redesigned the entire system using pre-assembled hydraulic modules with quick disconnect fittings. Installation time dropped from 40 hours to 4. By early October 1942, Schwendler's team had produced complete manufacturing drawings for what they called the F6F production model. The drawings violated Navy specifications in 147 specific instances. Every violation was documented with engineering justification, but none had been approved. The most significant changes involved structural redesign. Several fuselage formers were modified for easier manufacturing. Wing rib spacing was standardized. Skin panel shapes were simplified. Each change made production easier while maintaining or improving structural strength. Grumman and Swirbul faced a critical decision. They could submit the redesign to the Navy for approval, guaranteeing months of review and probable rejection. Or they could build prototype aircraft using the new design and demonstrate that mass production was possible without compromising combat capability. The gamble was enormous. Building prototypes without authorization would cost hundreds of thousands of dollars. If the Navy rejected the design, Grumman would absorb those costs and face possible contract cancellation. If pilots died because production shortcuts compromised safety, the company would face criminal liability. Swirbul authorized prototype construction on October 8, 1942. "We're betting the company," he told Grumman. "But if we don't take this risk, we can't deliver the fighters the Navy needs." Better to ask forgiveness than permission. The production engineering group immediately began fabricating components. They worked with Bethpage's machine shops to produce parts to the new tolerances. Every component was measured and documented. Any part failing to meet specifications was rejected and remade. The first fuselage built to production specifications was completed October 23rd. It used standardized panels that required no hand fitting. Assembly time was 32 hours compared to 80 hours for traditionally built fuselages. More importantly, measurements showed the production fuselage was actually more consistent dimensionally than hand-fitted versions. The first wing group followed on November 2nd. It bolted to the production fuselage perfectly on the first attempt, requiring zero adjustment. This single, successful fit validated Schwendler's entire concept. Precision manufacturing eliminated adjustment time. By mid-November, the first complete F6F production model was ready for flight testing. It was simultaneously Grumman's greatest achievement and greatest liability, an unauthorized fighter that could save or destroy the company. While Schwendler's team redesigned the Hellcat, Grumman broke ground on plant number 3. A purpose-built facility designed specifically for mass production. The site was adjacent to the existing Bethpage complex, allowing shared utilities and workforce, but the new building embodied revolutionary concepts borrowed directly from automobile manufacturing. Roy Grumman had studied Albert Kahn's work on the Detroit Arsenal tank plant. Kahn's designs maximized workflow efficiency and allowed rapid construction. Though Grumman couldn't afford Kahn's services directly, he hired architects familiar with Kahn's principles to design Plant No. 3. The main building measured 600,000 square feet under one roof. Unlike traditional aircraft factories with multiple work bays, Plant No. 3 featured a single open floor plan allowing flexible production layout. The design incorporated extensive natural lighting through sawtooth roof monitors, reducing dependence on electrical lighting. Construction proceeded at extraordinary pace. Groundbreaking occurred September 21, 1942. By November 15th, the structure was weathertight and equipment installation was beginning. This 60-day construction timeline was possible only through reinforced concrete construction methods that Kahn had pioneered. The facility's centerpiece was the moving assembly line, a concept never before applied to fighter aircraft. Schwendler designed a main line running 400 feet through the building's center. Fighter fuselages would ride on wheeled carriers, moving from station to station as workers performed specialized operations. The line included 22 primary stations, each designed for specific assembly tasks. Station 1 received bare fuselages from the fuselage subassembly area. Stations 2 through 7 installed internal systems, hydraulics, electrical, controls. Stations 8 through 12 installed the engine and cowling. Stations 13 through 16 attached wings and tail surfaces. Through 20 installed equipment and armament. Stations 21 and 22 performed final inspection and testing. Each station was staffed by small teams trained for specific operations. A worker at Station 5 installed hydraulic lines using standardized routing procedures. Another at Station 9 bolted the engine mount. Another at Station 14 attached the port wing. Each operation was timed, documented, and refined for maximum efficiency. The moving line concept terrified traditional aircraft workers. Craftsmen took pride in seeing a project through from start to finish. Assembly line work reduced them to repetitive operators. Many senior workers quit rather than adapt. Swirbul let them go, recognizing that mass production required different skills and attitudes. Replacing skilled craftsmen required developing an entirely new workforce. Grumman established training schools, teaching specific operations to semi-skilled workers. A typical training program lasted 2 weeks, far shorter than the years required for traditional aircraft work. The workforce transformation was dramatic. Housewives from Long Island suburbs learned to rivet aluminum panels. Farmers from upstate New York operated precision drill presses. High school graduates fresh from graduation installed complex hydraulic systems. By December 1942, Plant No. 3 employed 4,000 workers, 70% of whom had zero aircraft experience 6 months earlier. The supplier network expansion paralleled workforce growth. A fighter contains thousands of components that Grumman couldn't manufacture internally. Schwendler identified 237 supplier companies across 18 states capable of producing parts to the required tolerances. Each supplier received detailed specifications, precision gauges, and technical support. A machine shop in Connecticut produced landing gear struts. A forge in Pennsylvania supplied wing fittings. An electrical company in Massachusetts manufactured wiring harnesses. The entire network was coordinated through a central procurement office that tracked every component and flagged potential shortages. The first production F6F rolled off the assembly line October 31, 1942. The date was deliberately chosen exactly 9 months after McCain's initial call, though months ahead of the mid-1943 deadline. The aircraft was completed in 40 man-hours of final assembly time, compared to 200 hours for traditionally built Hellcats. The time reduction came from precision components requiring no adjustment, wings bolted on perfectly, hydraulic lines connected without modification. Engine installation took 90 minutes instead of 2 days. Quality inspectors found the production aircraft actually superior in dimensional consistency to hand-built versions. Flight testing validated the production methods. Test pilot Robert Hall flew the first production Hellcat on November 7th and reported it performed identically to hand-built prototypes. Subsequent test flights confirmed that mass production hadn't compromised combat capability. By December 1942, Plant Number 3 was producing 6 fighters daily. The production rate was doubling monthly as workers refined procedures and suppliers ramped up deliveries. Grumman's forbidden gamble was succeeding beyond even Swirbul's optimistic projections. January 16, 1943. USS Essex, operating east of the Solomon Islands. Lieutenant Commander John Raby led Fighting Squadron 9 into combat for the first time, flying 12 mass-produced F6F Hellcats fresh from Bethpage. What happened in the next 40 minutes would validate every risk Swirbul and Schwendler had taken. VF-9 encountered 18 Japanese Zero fighters escorting bombers targeting the Essex Task Force. The engagement was brief and decisive. Raby's squadron shot down 16 Zeros without times of tension, losing a single Hellcat. But the combat reports that reached Bethpage contained something more valuable than kill ratios. They praised the fighters' reliability. "Not one mechanical failure," Raby wrote in his after-action report. "Every gun fired when triggered. Every control responded precisely." These aircraft performed flawlessly under combat stress. This endorsement from combat pilots silenced remaining skeptics about production methods. The reliability stemmed directly from Schwendler's precision manufacturing. Hand-fitted components often developed problems under stress as custom adjustments failed. Precision manufactured components designed to exact tolerances performed consistently because they were built correctly from the start, not adjusted into acceptability. More combat reports arrived throughout early 1943. USS Yorktown's VF-5 reported similar experiences. USS Enterprise's VF-10 praised the Hellcat's maintainability. Carrier maintenance crews discovered that standardized components allowed rapid repairs. A damaged wing could be replaced in hours rather than days because any wing fit any fuselage perfectly. These combat validations reached Washington in February 1943. The Navy's initial order for 2,000 fighters suddenly seemed inadequate. Admiral Ernest King, Commander-in-Chief of the United States Fleet, reviewed Pacific Theater requirements and reached a stunning conclusion. The Navy needed not 2,000 Hellcats, but 12. The revised requirement arrived at Bethpage on February 23rd. Swirbul received the call from Admiral McCain, who had been promoted to Deputy Chief of Naval Operations for Air. "We were wrong about how many fighters we needed," McCain said. "We need 6 times more. Can you deliver?" Swirbul's response echoed his earlier confidence. "We'll figure it out." But the challenge was genuinely daunting. 12,000 fighters represented a 400% increase in total production requirements. Meeting this demand required not incremental improvements, but fundamental scaling of the entire production system. Schwendler and his production team analyzed every bottleneck. Plant Number 3 was producing 6 fighters daily in February 1943, approximately 180 monthly. Reaching 12,000 total production would require maintaining that rate for 5 years, or accelerating dramatically to complete deliveries sooner. The Navy wanted acceleration. War in the Pacific was intensifying. Every month of delay meant American pilots flying inferior aircraft, or flying no aircraft at all due to losses exceeding replacement rates. Grumman committed to reaching 20 fighters daily by the end of 1943. Achieving this required expanding everything simultaneously. Plant Number 3 was enlarged, adding 200,000 square feet of production space. A second assembly line was installed parallel to the first. The supplier network grew to over 400 companies across 32 states. The workforce expansion was extraordinary. Grumman employed 4,000 workers in December 1942. By June 1943, employment reached 12,000. By December 1943, 18,000 workers filled 2 shifts. By mid-1944, 25,000 employees worked 3 shifts around the clock. This workforce consisted overwhelmingly of people who had never touched an aircraft before the war. Women comprised 40% of production workers by 1944. Many were housewives whose husbands were serving overseas. Others were young women who had been teachers, secretaries, or store clerks before the war. The training system evolved to handle thousands of new workers monthly. Grumman established a dedicated training facility with full-scale mock-ups of every assembly station. New workers spent 1 week in classroom instruction, learning blueprints, tools, and procedures. They spent a second week on mock-ups, performing their assigned operations repeatedly. Only then did they move to the production floor. Production rates climbed steadily. 6 fighters daily in February 1943 became 12 daily by June. By September, 18 fighters rolled off the lines daily. By December 1943, Bethpage achieved 24 fighters daily, 520 monthly, exceeding the year-end goal. Continuous improvement drove these gains. Schwendler established a system where every worker could suggest improvements. A riveter who found a faster way to set a line of rivets would demonstrate the technique, and it became standard procedure within days. An assembler who redesigned a tool to work more ergonomically received recognition and immediate implementation. Final assembly time continued dropping. The 40 man-hours achieved in October 1942 fell to 30 hours by mid-1943. By December 1943, final assembly required 20 hours. By mid-1944, 15 hours. By early 1945, the most experienced crews completed final assembly in 6 man-hours. This represented a 97% reduction from the 200 man-hours required by traditional methods. The improvement came not from workers moving faster, but from engineers, eliminating wasted motion, simplifying procedures, and designing better tools and fixtures. The contrast with Japanese production was stark. Japan's Mitsubishi A6M0 remained in production throughout the war, but manufacturing methods stayed unchanged. Zeros were hand-built by skilled craftsmen using traditional techniques. Production peaked at approximately 350 aircraft monthly across multiple factories. Grumman's single Bethpage facility was producing 520 Hellcats monthly by late 1943, exceeding total Japanese Zero production. By mid-1944, Bethpage alone produced 650 Hellcats monthly. The production differential was becoming a strategic weapon. Japanese industry couldn't respond. They lacked the machine tool precision required for interchangeable parts manufacturing. Their supplier networks couldn't coordinate production across hundreds of companies. Most critically, their engineering culture viewed aircraft as craft products requiring master artisans, not industrial products suitable for mass production. By December 1944, Grumman had delivered over 8,000 Hellcats. The impossible goal of 2,000 fighters that had seemed absurd in September 1942 was exceeded 4 times over, and production continued accelerating. June 19, 1944, 450 miles west of the Mariana Islands. The largest carrier battle in history was about to validate not just the Hellcats' combat capability, but the entire philosophy of mass production warfare. Task Force 58 under Admiral Mark Mitchell deployed 15 aircraft carriers containing over 900 aircraft. Of these, approximately 600 were F6F Hellcats, every single one built using Schwendler's mass production methods. Facing them was the Japanese first mobile fleet, with 9 carriers and approximately 450 aircraft. The Japanese force included many of their finest remaining pilots, though pilot quality had declined since early war battles. More significantly, Japanese aircraft, particularly the Zero, remained craft-built using traditional methods. Each plane was unique, requiring skilled maintenance and custom repairs. The battle began at 10:13 hours, when American radar detected the first Japanese strike wave. Hellcats from multiple carriers launched immediately, vectored by fighter directors watching radar screens. This coordinated response was possible because the Hellcats were reliable and available in overwhelming numbers. The engagement that followed became known as the Great Marianas Turkey Shoot. Over 2 days, American Hellcat pilots achieved the most lopsided aerial victory in naval history. The final tallies told the story with brutal clarity. Japanese losses exceeded 476 aircraft. American losses totaled 29 aircraft. The kill ratio was 19-1 in favor of the Hellcats. These numbers reflected not just superior pilot training or aircraft performance, but the strategic advantage of mass production. Task Force 58 could afford to keep hundreds of Hellcats in the air because hundreds more were being built at Bethpage weekly. Damaged aircraft were replaced immediately from carrier spare aircraft inventories. The Japanese had no such luxury. Every Zero lost represented months of skilled craftsman labor. Replacement aircraft arrived slowly, often taking weeks to reach forward areas. Maintenance was complicated by each aircraft's unique characteristics. Parts weren't standardized, requiring custom fitting even for routine repairs. Lieutenant Commander Paul Bowie, leading VF-16 from USS Lexington, shot down 6 Japanese aircraft on June 19th alone. His combat report noted something significant beyond the kills. Every Hellcat in my squadron performed flawlessly. No mechanical failures, no gun jams. We focused entirely on fighting, not managing equipment problems. This reliability advantage came directly from precision manufacturing. Guns that were assembled to exact tolerances using interchangeable parts functioned consistently. Control systems, built from standardized components, responded predictably. Engines assembled from precision parts ran reliably under combat stress. Commander David McCampbell, leading Air Group 15 from USS Essex, became the Navy's top ace during this battle. He eventually scored 34 confirmed kills, but his post-war interviews revealed something more interesting than individual achievements. "We won because we had more fighters that worked better," McCampbell explained years later. The Japanese might have had skilled pilots, but they were flying craft-built aircraft that broke down. We were flying production aircraft that just worked, and when we lost one, there were 10 more being built that day to replace it. The Battle of the Philippine Sea marked a turning point where mass production became visible as a strategic weapon. The Japanese first mobile fleet was effectively destroyed as a fighting force, losing 3 carriers and most of its aircraft. It never recovered. American losses were negligible and were replaced within weeks. Admiral Mitchell's after-action report specifically mentioned production capacity. Our victory was enabled by material superiority. We had sufficient aircraft to maintain continuous combat air patrols, launch multiple strike waves, and absorb losses without degrading capability. This material advantage stems from American industrial production. The Navy's Bureau of Aeronautics analyzed the battle and reached conclusions that validated Swirbul's original gamble. A memo dated July 8, 1944 noted that mass production methods have proven combat effective. The F6F demonstrates that precision manufacturing actually improves reliability compared to traditional hand-fitting. Production quantity enables tactical flexibility impossible with limited aircraft availability. Back at Bethpage, workers followed battle reports with pride. They understood that the fighters they built weren't just machines but tools enabling American victory. Production motivation increased, absenteeism dropped, quality metrics improved. Workers took personal ownership of combat success. Grumman management shared battle reports throughout the plant. Photographs of victorious pilots appeared on bulletin boards. Letters from squadron commanders praising aircraft reliability were posted in assembly areas. Workers saw direct connections between their daily tasks and combat outcomes. The strategic implications extended beyond single battles. By mid-1944, American carriers could operate aggressively because losses could be replaced quickly. Japanese carriers, facing irreplaceable aircraft losses, became increasingly cautious. This operational tempo differential compounded American advantages. Production statistics from June 1944 showed Bethpage building 650 Hellcats monthly. In the same month, total Japanese fighter production across all types and manufacturers was approximately 800 aircraft monthly for the entire nation. A single American factory was producing 80% as many fighters as the entire Japanese aviation industry. This production differential made prolonged war unwinnable for Japan. Even if Japanese pilots achieved favorable kill ratios, which they didn't after mid-1944, American replacement rates exceeded loss rates by enormous margins. Japan couldn't sustain attrition warfare against American industrial capacity. The Battle of the Philippine Sea demonstrated these mathematical realities in combat. 600 mass-produced Hellcats overwhelmed 450 craft-built Japanese aircraft through reliability, availability, and numerical superiority. The battle was won in the skies over the Marianas, but the victory was forged in the factories of Long Island, where Schwendler's forbidden blueprint had transformed fighter production from craft to industry. August 15, 1945. Victory over Japan Day. When production finally ceased at Bethpage, the final tally revealed an achievement that had seemed impossible just 3 years earlier. Grumman Aircraft had delivered 12,275 F6F Hellcats to the United States Navy and Marine Corps. These weren't just numbers on production reports. Each Hellcat represented lives saved, battles won, and strategic advantages gained. But the numbers themselves told a story about how industrial methods had transformed warfare. 12,275 fighters in approximately 34 months meant Grumman averaged 361 Hellcats monthly across the entire production run. Peak production in March 1945 reached 705 aircraft. That single month, more than 23 fighters daily from a facility that had produced 3 monthly just 30 months earlier. The cost differential was equally striking. Traditional aircraft manufacturing methods produced fighters costing $150,000 to $200,000 per aircraft. Hand-fitting, skilled labor, and long production times drove costs upward. The mass-produced Hellcat cost approximately $50,000 per aircraft, including engine and equipment. This 3-to-1 cost advantage meant American industrial capacity could produce 3 fighters for the same investment required for one traditionally built aircraft. The strategic implications were profound. Japan couldn't match American production even if Japanese factories achieved equal efficiency, which they never did. Comparison to other American fighters illustrated Grumman's achievement. Republic Aviation produced 15,660 P-47 Thunderbolts from 1942 to 1945, but across multiple factories. North American Aviation built more than 15,000 P-51 Mustangs, again using multiple production facilities. Grumman's Bethpage plant alone produced 12,275 Hellcats from a single location. The Vought F4U Corsair, the Hellcat's contemporary and competitor, achieved total production of 12,571 aircraft, but production was split between Vought, Goodyear, and Brewster across multiple factories in 3 states. Single-facility production at Grumman's at scale was unprecedented. International comparisons were even more dramatic. Germany produced approximately 33,000 Messerschmitt Bf 109 fighters from 1939 to 1945 across dozens of factories, many using slave labor. Britain built approximately 20,340 Supermarine Spitfires from 1938 to 1948 across multiple production sites. Japan's fighter production totaled approximately 64,000 aircraft of all types, from 1941 to 1945, but this included multiple models across numerous manufacturers. The Mitsubishi A6M0, Japan's primary naval fighter, achieved total production of approximately 10,430 aircraft across the entire war, fewer than Grumman's single-facility Hellcat production. These production differentials reflected fundamental philosophical differences. Axis powers viewed aircraft as specialized, military equipment requiring traditional manufacturing. American industry treated fighters as complex mechanical assemblies suitable for mass production using automotive principles. The workforce story behind these numbers was equally remarkable. Grumman employed approximately 1,200 workers in September 1942. Peak wartime employment reached 25,300 workers in March 1945. This meant Grumman hired approximately 24,000 new employees in 30 months, while simultaneously increasing per-worker productivity. Women comprised the largest demographic shift. In September 1942, women represented less than 5% of Grumman's workforce, mostly in administrative roles. By 1944, women comprised 42% of production workers, performing every manufacturing task, from riveting to final assembly. Rose Monroe, who worked at Grumman from 1943 to 1945, later recalled the transformation. "I had never touched an aircraft before the war. I was a housewife. After 2 weeks of training, I was installing hydraulic systems. After 6 months, I was training new workers. The work wasn't easier than traditional methods, it was smarter. Minority employment also increased dramatically. African American workers comprised approximately 18% of the workforce by 1944, working in all production roles. This represented significant progress in an era of widespread discrimination, driven by urgent wartime needs and enlightened management, recognizing that talent was distributed without regard to race or gender. The training system that enabled this workforce transformation became a model studied by other manufacturers. Grumman's 2-week training program proved that complex manufacturing could be taught rapidly if processes were properly designed and documented. This challenged assumptions about skilled labor, requiring years of apprenticeship. Recognition for William Schwendler's wartime contributions came slowly. During the war, secrecy shrouded his work at Grumman's Bethpage plant, where production innovations turned aircraft manufacturing from craft to science. Only in 1947 did the Navy publicly honor him with its highest civilian award, the Distinguished Public Service Award, citing his revolutionary production engineering. 2 years later, the Society of Automotive Engineers granted him its Medal of Merit, praising his adaptation of automotive principles to aircraft production. In his typically modest words, "We simply refused to accept that aircraft had to be built slowly." Schwendler's impact reached far beyond Grumman. Boeing studied his methods when organizing B-29 Superfortress production. Douglas adopted similar practices for the A-26 Invader, and North American used them to mass-produce the P-51 Mustang. Post-war civil aviation borrowed the same philosophy. The Douglas DC-6, Lockheed Constellation, and Boeing Stratocruiser all used modular assembly, standardized components, and precision tolerances derived from wartime innovations. The greater legacy was philosophical. Schwendler proved that complex machines could be designed for manufacturability without sacrificing performance. His principle that design and production engineering must cooperate from the outset became a foundation of modern industry. By 1950, every major U.S. aircraft maker had a production engineering department modeled on his. The 12,275 Hellcats, built in only 34 months, were not just statistics, but evidence of a new way of thinking, industrial efficiency triumphing over artisanal tradition. The men behind that achievement, Roy Grumman, Leon Jake Swirbul, and William Schwendler, each saw their vision reshape aerospace. Grumman guided his company into the space age, producing the Apollo lunar modules and F-14 Tomcats before retiring in 1972. Swirbul, Grumman's risk-taking president became a business school legend for authorizing forbidden blueprints that bypassed bureaucratic constraints. He led the company until his death in 1962. Schwendler remained chief production engineer until 1958, later consulting for Boeing, Lockheed, and Douglas. Aviation Week's obituary in 1979 summarized his influence simply: "Every American aircraft built after 1943 bore his mark. The Hellcat itself outlived its war. Reserve squadrons flew it during Korea, where its toughness and reliability made it valuable for ground attack. France used Hellcats in Indochina until 1954. Argentina and Uruguay kept them operational into the early 1960s. 2 decades after the first Bethpage Hellcat rolled out, the design still served nations around the world." Meanwhile, Schwendler's production philosophy spread across the U.S. aerospace industry. Boeing's B-47 Stratojet and Douglas's A-4 Skyhawk were designed with manufacturability in mind, drastically reducing costs and build times. North American applied the same logic to the F-86 Sabre, producing nearly 10,000 of America's first swept-wing jets between 1949 and 1956, numbers unthinkable a decade earlier. Modern fighters continued the lineage. The F-16 Fighting Falcon, introduced in 1978, was engineered from inception for efficient production. Its 4,600-unit output would have been impossible without Schwendler's principles. Today's F-35 Lightning II represents the ultimate evolution: 300,000 parts manufactured worldwide to micron tolerances, assembled robotically in days. That process, the seamless coordination of design, production, and logistics, descends directly from the thinking born in that locked Bethpage room in 1942. Historians often emphasize strategy and leadership, but the Pacific War was won as much by production as by tactics. Japan could not replace losses. America could. Industrial capacity, guided by engineers who understood manufacturability, became a decisive weapon. U.S. shipyards launched fleet carriers in 17 months, destroyers by the dozen, and tanks by the thousands, all through mass production methods inspired by Schwendler's wartime breakthroughs. Breaking the rules was never his goal. Achieving results was. The forbidden blueprint existed because traditional methods could not meet wartime needs. Schwendler violated specifications not from defiance but from clarity of purpose. Rules serve outcomes, not the reverse. His pragmatism became a guiding ethic for post-war engineering and management alike. That philosophy endures beyond aerospace. Automakers refined his mass production logic into today's precision manufacturing. Consumer electronics, medical devices, and even smartphones' complex modular products, built by semi-skilled workers to microscopic tolerances, owe their existence to principles first proven at Bethpage. Every time a product is redesigned for easier assembly or mass-produced without sacrificing quality, Schwendler's legacy operates silently in the background. When he died in 1979, his obituary quoted a remark from 1948. Asked if he feared violating Navy specifications, he replied, "I was more worried about American pilots dying in inadequate numbers of inferior aircraft. Sometimes you have to break small rules to serve larger purposes. That's not rebellion, that's engineering." Those words capture the essence of the forbidden blueprint. It wasn't about defying authority, but about redefining possibility. Schwendler saw that the true barrier to victory wasn't enemy skill, but production limitation. By questioning assumptions and re-engineering the process, he made the impossible achievable. The 12,275 Hellcats produced between October 1942 and August 1945 were more than airplanes. Schwendler's team didn't just design a fighter, they designed a system that could build fighters faster than anyone thought possible. Their success reshaped industry, strategy, and even peacetime manufacturing. That lesson remains timeless. Every modern production challenge, whether aerospace, automotive, or electronics, echoes the same truth. When engineers think boldly and design with manufacturability in mind, limits vanish. The spirit of the Hellcat lives not in museums but in every assembly line where precision meets volume and where questioning how it's always been done leads to transformation. William Schwendler was the engineer who broke the rules to save lives. His forbidden blueprint turned necessity into innovation and established a philosophy that continues to guide modern industry. In that small, locked room at Bethpage in 1942, he and his team proved a simple, enduring idea. With clear vision, courage, and sound engineering, even the impossible can be built. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch, and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.